we got that solved. Okay, today this is the last of our series on ag energy. Today we're pleased to have Dr. Rebecca Larson with us, who's an assistant professor here at the University of Wisconsin-Madison. Her area of concentration is bio-waste, and she actually has lots of little 55-gallon drum digesters going in her lab, trying to figure out what feedstocks work best, and et cetera. So we'll turn it over to her, and we're going to learn a little bit about on-farm energy production using biodigesters. Thank you.
Hey, thank you, Scott. Again, my name is Becky Larson. I'm in the Biological Systems Engineering Department. I do a lot of bio-waste engineering. Typically, that's in the glamorous world of manure. And today, I'm going to talk about on-farm anaerobic digestion systems. I don't know if typically you guys do questions throughout or if you wait to the end. I am more than willing to clarify things or adapt what we're talking about here if there's specific interest.
Yeah, typically they can type them in, and if it's something, I'll try to interrupt you.
Okay, great, perfect. Okay, let's see if I can get this to go to the next slide. All right, so just a little background. I'm sure a lot of you are aware, if you're tuning in here today, that we have quite a few dairy cows here as well as other animals. We have a lot of manure produced here, and a lot of people have historically thought of that as a waste product, but now we're moving to the idea that it has quite a bit of value, and one of those values is potentially for biogas. There's a lot of potential impacts from manure and some of the other byproducts, ag byproducts that are produced, but we need solutions which make economic sense, which can protect the environment, as well as provide support for our ag economy. Okay, so I just want to throw in this slide here so you can get an idea of anaerobic digestion in the United States. You can see Wisconsin there. It looks like it has about 26 digesters. This is from the US EPA AgStar, which does a lot of on-farm digester work in the country. I'd say our number's a little bit higher than that, 26. And I know that there's still quite a few projects that are being implemented in the ag sector as we speak. You can kind of see there the energy yield from that. You can see total around the United States that Wisconsin is the leading state in on-farm anaerobic digestion systems. I will point out that some of these others, maybe on the East Coast in California, are growing significantly, particularly in California due to some changes that make systems potentially more profitable, as well as up in the northeastern area. They have policies that promote these types of systems to be implemented there. Here's kind of a breakdown of different types of systems within the U.S. You can see the major component of those is mixed plug flow and completely mixed systems. There's lots of different types of digesters. We'll talk a little bit about more what those are in a moment, but there's many different ones. It's different here compared to other countries of what this breakdown kind of is, but many of them work on the same, all of them work on the same principles, which are pretty basic and we'll discuss in a moment. Okay, so why is it that why are we even talking about this? Why should we want to install a digester? A lot of people talk about energy independence, you know, the ability to produce energy within the state instead of having to input energy from other areas. Mitigation or reductions in greenhouse gases. All manure, regardless of how you store it and what's going to happen, particularly when it's anaerobic, you're going to get releases of methane and other greenhouse-causing gases. And when we shift to an anaerobic digester, although we're combusting that, we are, in a sense, not releasing methane, which has a much higher global warming potential than some of the other, than like CO2, which it's then released as. So we're really changing the form of it, and therefore we're mitigating some of the impacts of that. It can give you some flexibility in manure management. So there is possibility of some of the components that are add-on of changing what the characteristics of the manure might be that might, depending upon what kind of system you're using, might be helpful in reducing some of the impacts of manure application. We'll talk about that in a little bit too. I do want to mention there's a lot of myths about what digesters can do in terms of manure management. We do see a reduction in odor and pathogens. That's been verified by a number of studies. Odors are difficult to measure, difficult to quantify, but we really have seen in a number of different ways that you do get some odor reduction. It, of course, varies. Manure is never, or rarely ever, doesn't smell like manure. You're still going to have some odors, but the impact seems to be much reduced. There's potential for asset stream, so not only could this be environmentally friendly, there's the potential to replace bedding. That's been pretty important in economic tipping fees for additional substrates aside from manure. And then the potential for environmental credits. You know, a while ago I would have said, besides some availability from federal government things, there wasn't a lot out there, but it looks like in California they're kind of developing their own carbon market where you might be able to get some profits from there. So one of the big things about digestion we're going to talk about today is a little bit about the technology and how it works. But one of the important things that comes up all the time is, are these systems profitable? I'm going to talk a little bit about why I've seen some systems that have been able to have short payback periods and why I think some systems have had much more trouble in doing that. And then a little bit about what digesters can't do. You know, I see a lot of times digesters have been shown to reduce phosphorus or change phosphorus, and that's just not true. So they can later in other pieces that are typically added to digestion systems can aid in flexibility in manure management, but there's no removal or disappearance of phosphorus through the digestion system itself. Okay. So let's start with what is anaerobic digestion. It's a biological process. We break down organic materials, typically called feedstocks. Sometimes we'll call them substrates. We do this without oxygen, so it's an anaerobic system. And the microorganisms that are naturally occurring within manure, and some other digestion systems, they might have to add additional waste. A lot of times they use manure to provide this microorganism population, which does this, but in manure they're naturally occurring. And what they do is they break down these organic materials, and part of this process releases methane and carbon dioxide. So this is just kind of an idea to kind of give you a process flow diagram of how digestion works, right? We put feedstocks into this slurry tank or the digester, and this when we can limit or eliminate any oxygen from the system, the microorganisms will naturally produce this biogas. I would say there's not much going on in that tank besides it's a big tank where we store manure and we don't let oxygen into the system. Digestate is then typically separated. I don't think there's any systems in Wisconsin now that have a digester on an agricultural setting that don't have a separator following it. So the separator then can take this digestate or the manure or other feedstocks that have been through the digestion process and separate it into a liquid and a solid component. The biogas is then used for a variety of different things. Mostly here in Wisconsin, we see a lot of electricity production. Okay, so here's kind of what that looks like, right? So on the collection feedstock side, we typically have some kind of manure collection system that's done quickly. So each day it's pumped, scraped or collected, however that might be set up on the farm. And as quickly as possible, we try to pump that into the digester itself. The longer you let it sit there, the more it degrades not in the system, so then you get reduced biogas production. So the main thing here is collect multiple times a day, feed your digester multiple times a day, and you'll get try to optimize your biogas production. Here you can see a plug flow system. We'll talk a little bit about the differences of them, but in here the manure is collected, and then there's a headspace where the biogas is collected, and then that is sent to a generation system. And then you can see down here in the lower corner we have a separation system. Here it's a screw press. Just to kind of give you a visual of what we're kind of through an anaerobic digestion process. Okay, when we're talking chemistry and biological processes, you can start to pretend that it's super complicated, even though it really isn't. Right? So we have these complex polymers. We have hydrolysis. And then we have and then we have the methanogen phase. So we really have these 4 stages that are taking place in the digester itself. Okay, these are different types of bacteria that break these down. So step by step, we're just going from complex polymers to sugars, amino acids, peptides, into short chain volatile organic acids. Then we're going into acetate and CH4 and CO2. So it's a pretty, you can make it look complicated with some bigger words, and there's more components to each of these, but generally we're going through 4 major stages, and the last one being the methanogen production. All right, so when we produce biogas, what we call biogas, some people call digas, we primarily have 2 components. So one is the methane and one is CO2. The methane obviously is the portion that we're interested in, and then we either have to have a system that can handle the CO2 component or remove that later. There is a problem. The one issue is that we have some trace elements, and the one that is the major problem in biogas production is something called hydrogen sulfide. Hydrogen sulfide, when mixed with moisture, can produce sulfuric acid. And you can see quickly, very quickly, if you have a significant amount of hydrogen sulfide production, the sulfuric acid will be produced and eat through systems right away. So that's a major issue and hurdle for those running these systems to combat. The biogas itself, though, can then be used for heat, so simply for burning, probably the most basic. It can be put into a genset to produce electricity. It can be cleaned up to produce what you would consider natural gas. And then, it can be used as a variety of other sources. These are maybe the most common, and I'll talk a little bit about why they're common and which ones are common, mostly electricity, why that's common, where we might be going. So the digestate, again, we make a fiber product. We use it as nutrients. The majority of it is used as fertilizer. So different types of digester systems. Up here in the left-hand corner, you can see a covered lagoon. So in this case, we just have a lagoon. We put an impermeable cover on top of it, and we're able to collect the biogas that's naturally produced in these types of systems. In these systems, they are a little less expensive, so they're a little bit more cost-effective. However, there's no heating elements, so if you're in a colder climate, biogas production might be reduced during certain times of the year. Additionally, if you have certain types, if you see settling in the type of manure that you have, it can be problematic when you're trying to empty these out to apply manure. Maybe not every year, but it can become an issue. Plug flow, which is down here in your lower left down here, just kind of goes in a U-shape. Just as it sounds, a plug moves through the system. So if you think of a long tube, and in one end I put manure in, and that manure flows as a plug through the tank. You can really design the retention time through the system. You can imagine that's exactly what a plug flow is. A completely mixed system are some of these larger above-ground tanks that you see around Wisconsin and other places. These are just large tanks, but they have mixing systems, and the influence enters in one place, it's all mixed up, and the effluent exits another. There's more complicated systems, fixed film and induced sludge blankets, etc. What really the objective of a lot of those systems is to just increase surface area for microbial populations to go on, right? So if we want to maximize biogas production, the more microbial pieces that we have, populations we have, the more microbial biomass we have, the greater amount of biogas you'll produce for any specific feedstock. So what these systems are trying to do is put some kind of media in there to promote microbial growth within them. They're not as common right now. They're a little bit sometimes more difficult to operate, typically due to clogging and some other issues. All right. I think I highlight these two again because the anaerobic, the completely mixed and the mixed plug flow are maybe the two most common systems we see around Wisconsin. And a lot of these plug flow systems, there's a manufacturer here in Wisconsin that has done the majority of these systems. And then there's a variety of maybe a larger variety of companies out there who have completely mixed systems. Okay, the next step in the digester kind of system, when we're talking about the whole system, is the separation system. So commonly folks use screw presses. This is an important step, and I'll talk a little bit about what that means for Digestate in a minute. But after you flow through the digester, the majority of them have these either a screw press. Here's a picture of a centrifuge while it's open. You can see that they just separate the solids from the liquids. So then typically the biogas use, there's three kind of main uses for biogas, well maybe four. One is burning. We don't see a whole lot of that, but it is done in some areas. A lot, even at this point, might even just flare gas and not necessarily produce any products. We don't like to see it, but sometimes the additional systems are expensive. So the most common thing we see in Wisconsin on on-farm system is a generator or combined heat and power producing electricity. It's most common. There's a lot of companies that produce these particular systems. They are expensive. You need the generator to be specifically designed to handle biogas. As I mentioned that hydrogen sulfide previously, that can cause a lot of issues in your generator. As people have learned a little bit more, that maintenance is pretty intensive on these systems. But the more maintenance you do, the more often you can limit shutdown and other issues that you might run into. Natural gas, so cleanup and then injection into like a natural gas pipeline, that's a little bit more uncommon because the cost for cleanup is extremely high. So the systems exist. There's lots of technology out there that can do almost anything you might want it to do with biogas. Unfortunately, at this time, it's just too expensive to clean it up, particularly due to the low cost of natural gas right now. The next thing, compressed biogas, has maybe generated a lot more interest of late. There is still the high cost for cleanup in this particular system because you have to remove the CO2, the hydrogen sulfide, et cetera, and really make the methane extremely pure, above 99%, somewhere in there. So just like natural gas, its uses, it still has that high cleanup cost. In this case, there's been a lot of interest because we've seen, in this lower right-hand corner, they've designed a system for landfill. So this is a smaller scale system to compress the biogas and use it as vehicle fuel. So using it as vehicle fuel really increases the potential revenue for these systems. So we see that there is more interest in this area because even though the high cost of cleanup, we might make enough money to pay back that initial cost and really increase our revenues for this system. I write here that there's limited information for these types of systems because there aren't many that are integrated into on-farm systems in the U.S. So on the right, I had that picture of the compressed system for a landfill. That was maybe one of the smallest made by that particular company. They typically do really large installations. But there has been one design on one facility in Indiana. They're still evaluating and seeing how that's working for them. But I think in the near future, we'll see quite a few more of those systems. When we're talking about digestion, there's some key elements that are important. One is temperature. There's lots of sensors and controls out there to help people maintain temperatures. A lot of times the biogas is used to maintain temperatures, either one, by burning it in a boiler and then heating, heating the digester with that, or potentially using some of the excess heat produced by the generator to then heat the digester itself. Typically, we keep the systems at about 100 degrees Fahrenheit if they're mesophilic. A thermophilic system is a little bit higher, around 135. Thermophilic systems are a little bit more money to heat, obviously, because of the higher temperature, but they have much shorter breakdown periods. So, for example, manure in a mesophilic system at 100 degrees might take around 25 days to break down, so the retention time is pretty long. In a higher temperature, you can maybe do that in 5 days, so it might reduce the cost of your system. The pH, we have to kind of pick this pH range. Remember when I said there were those four main processes that were happening? Although it's not the ideal pH range for methanogens that we try to operate at, we operate pretty much at a neutral kind of pH. We want to kind of get an overlapping pH range for the variety of different microorganisms that have to go through all of those four stages. Maintaining those microorganism populations, again, is important. The feedstocks you choose, you have to be careful of toxicity and making sure that the microorganisms can handle that and what kind of loading rate you apply. Mixing is important. If you can imagine, these microorganisms can't swim around and be in contact with the nutrients and things that they need, so a little bit of mixing can be important to increase your biogas productivity and increase degradation. Again, you have to limit the toxicity, which can be quite damaging to the microorganisms. And then it's really important that they have the micro and macro and nutrients that are needed for the survival of these microorganisms. Manure is a good source of a lot of different nutrients that they need. There's been work saying there's a few other things that they might need, but generally manure provides what is needed by the microorganism population. And then HRT, I kind of say, is a hydraulic retention time, so designing your system, its flow path, what's happening, that's kind of part of the engineering design that's done by the company from which you purchase your system.
Becky, can I interrupt just a second? What are some of the common toxicity problems you run into?
So we see a lot of like copper sulfate, a foot bath at dairy facilities. So copper can be toxic at high concentrations. It can handle a little bit, but not everything. Some other things that we see, in particular, taking on additional substrates that might have some issues. There's some stories about how someone was receiving a certain food byproduct waste for months and months and everything was fine. But then they didn't realize that this company will do batches, so for months they'll run one product and then they'll do another. And the second product had some additional pieces that just didn't work well with the microorganisms and that shut their whole system down. One of the other big ones is rumensin. So rumensin is given particularly to dairy animals to suppress methane production within their digestive tract. You can imagine if you're giving your animal something to suppress methane production when you're wanting to produce methane later, it can be quite toxic to that type of thing. I just kind of wanted to show you how important here organisms are in biogas yield. So I'm not going to talk a ton about this, but there is work being done to look at, you could see here the control, and then they augmented some of these to get into these green bugs, and you can see it really increased the production of biogas in these, or methane in these systems. So, it is important that different community structures can really increase biogas production, but I think at this stage of the game, that's a little beyond where a lot of operators might be. Okay. So I want to talk a little bit more about feedstock. So there's lots of different types of feedstocks. Obviously, I talked a bit about manure, but there's lots of other things people use in these types of systems. Cheese waste, food processing waste, all kinds of manure, vegetable waste. Anything that's organic that you can think of that might not have some potential issues with certain kinds of chemicals or detergents or other things. This is probably the most common thing you'll see if anybody giving a general biogas talk. We use it all the time, but it just is here to show you an idea of what these different feedstocks, why we use different feedstocks. You can see that they all have different potential of biogas production. So down at the bottom, we have kind of manure down here. You can see that's really low producing gas potential per ton, right? So the why we use manure is that it's readily available. Typically doesn't cost us anything. If you put the facility where it's produced, you don't have to transport it. It's in high abundance. But then when we talk about these additional substrates, there's really potential to increase with small additions to really increase biogas production. So that's why a lot of people are really interested in some of these other potential feedstocks. When we're looking at feedstocks, you really have to know what to use. So one, you really need to avoid toxicity, as I mentioned before. There are now brokers who will deal with digesters and say, you know, give us 30% of your digester and we'll provide the feedstock for you. It's a little risky maybe sometimes. A lot of people are quite nervous about that because you're really saying to the supplier, okay, I trust you and you really know what it is that can go into the digester. You really need to evaluate additional substrates. So what I always recommend is we have lots of these little systems that we can do really small bottles just to look for toxicity or to try to determine what optimum ratios might be. It's really not something at this time that we can calculate ahead of time. We really have to do it on a sample-by-sample basis to determine what's going on. Some of them require pre-processing, so that's another issue that might be costly. If I have to process some kind of larger fiber material or anything that might require some kind of pre-processing, particularly a lot of them are to chop them up into finer pieces that can be expensive. What will the substrates do to the digestate? So after I put in a bunch of, you know, high salt things, remember I have to then land apply this. So I have to be careful of what some of these substrates are going to do to the digestate depending upon what I'm going to use it for. If I'm using the solids for animal bedding, for example, I need to be careful what I might add into there that might impact herd health. And then I heard a producer say this recently that I really like. The rule of thumb is that it must be worth more than the cost of spreading any additional substrate. So if you really imagine if I'm taking on an on-farm scenario or I'm taking on an additional feedstock into my digester, I really need to then evaluate that my application costs are going to be less than what they're paying me to take that waste. So you can imagine if I'm not receiving anything and I'm only producing biogas, then that biogas has to be enough to pay for not only the structure to produce the biogas, but also for the land spreading afterwards. You can see in this revenue that Bob Nagel gave recently at the Manure Summit. This was some of the cost information that he provided, which was really great of him because we don't see a lot of this. And you can see how important the tipping fees were for them in being successful. That's a significant amount of money for them each year for tipping fees. So it's really important that you measure how, you know, I see a lot of times people, if you take additional substrates just for the biogas and not factor in the cost of application later, you might be in trouble. The other thing is I tell people not everybody might have access to these test systems to look at everything. And sometimes you think, I'm pretty sure there's not going to be anything toxic. If you're willing to do that, the really important thing is to load a new substrate really slowly. So as I add something slowly, the microorganisms really can adapt to that. But you need to give them time, and you need to, if you see something happening, if you're loading slowly and there is toxicity, you might be able to limit the amount you add before anything catastrophic and you get a complete failure of your system. I just want to show you with those systems what kind of some of the testing we do. You know, we do these little small-scale laboratory tests called biomethane potentials, or BMPs. You'll see these a lot of you see more and more labs now offering these for a fee. The one thing I want to mention is you can see you can look at kind of batch tests. So, from looking at this, I say, okay, rice hulls up here produces much more biogas than maybe glycerin down here. I would be careful and weary of how much stock I put into these types of tests. They're useful, but you really need to evaluate what's going on. There could be a lot of other issues, what ratio you're adding. Maybe if I change the glycerin ratio or if I added some buffers depending upon what's going on, I would imagine that might be a really high-producing feedstock. So it really depends upon ratios. They're useful, but be careful what you take from them would be my general outtake there. Okay, again, mixing. So what we see a lot now with mixing is that it's still done on a trial and error basis. So we have these large digesters. They're mixing the systems to increase biogas production. We know from testing that mixing all the time is too often and actually decreases biogas production. Not mixing at all also is not optimizing the system. So we know it's some kind of intermittent mixing that really can increase biogas production. Unfortunately, there's not a lot to be said more than that. We're doing some testing. Other folks are doing testing to try to figure out and model and see why that might be and get a better understanding of how often you need to mix. But one, there is a cost associated with mixing, so there's an electrical cost. And people really need to do some experimentation to figure out what the best mixing regime is. A lot of times we'll see people do 15 minutes on, an hour off, half an hour on, 2 hours off. It really varies from system to system and how much they've been willing to go through some of the evaluation steps. A lot of people get to a point where they feel it was better than nothing, and so that's where they're at for now. The next thing I want to talk about a little bit is the digestate. So what happens to manure as it goes through the system? To me, this is really important because this is the area where there's just a lot of conflicting opinions, and I would say a lot of them are really not correct. What happens through the digestion is you can think of the tank of manure going in and coming out. It's a closed system, right? So we're not losing any manure. We are producing some biogas, so we're losing some carbon there. Maybe minimal amounts of nitrogen, something you probably can't even measure on a regular basis. And we're not losing any phosphorus. So into a digester, out of a digester, phosphorus stays the same. This is not a phosphorus solution technology. Right? I see that mentioned incorrectly a lot of times. So the digester itself does not have any impact on phosphorus within the system. We do see some changes in nitrogen. Not the total amount of nitrogen, but the form that it's in. So we have a lot of conversion from organic nitrogen into ammonia, which I'll show you in a minute. That can be positive and negative depending upon what you're looking at. One, when we convert more to ammonia, we can see greater volatilization when I'm storing and land applying, but then I may have more availability to plants. At this point, there's been some work that's been done, but I would say we don't exactly know all the trade-offs that are going on when that happens. The big thing is the solid-liquid separation. I would say this is the area where you start to be able to get some type of manure management benefit. But there is a point to be made that you could install a solid-liquid separation system without a digester. So you really need to evaluate these two technologies for the basis of what they do separately. Okay, so one of the things that we've done recently, and this is a study from New York, but we've also confirmed this with some testing here in Wisconsin, is that we do get some significant reduction of different pathogens. And I don't have time here to go through all of our data from our recent study, but we looked at about 9 different farm systems in Wisconsin, 7 of those with digesters, and looked at what the disruption was. Here, a lot of the work's been done with indicators like coliforms, but in this new study that we did, we looked at a lot of additional parameters, things specific to herd health issues and human health issues. And we've seen kind of what you expected. You do get in this 90 to 99.99% reduction, but sometimes the concentrations are so high initially that even with that significant reduction, there still can be potential for issues because the concentrations can still be significant. Nutrients, again, this is like a total nitrogen TKN. You can see fairly similar here. Okay, so you can see that this has been pretty even. Nitrogen, I'd say these differences, how minor they are in and out of a digester, have been due to the method of analyzing. So we get very little changes to really see that. I see there's a question there. Manure can raise soil organic matter. Is there enough carbon left in the manure after digestion to improve soil carbon? So there is still carbon remaining in the manure. Obviously, it's quite reduced. I have a student who's working right now on evaluating kind of carbon changes and where they kind of end up in this life cycle. But I still, there's still a benefit to soil, and it really depends upon the digestion process of how much we lose. I just wanted to show you here that there is that increase in ammonia that I talked about. So we have a change from organic nitrogen to ammonia in most of these systems. And again, there's those trade-offs that are going on. It's really hard with nitrogen. I was recently at a conference where they kind of said, climate change is a big issue right now, but nitrogen is really going to be the next big issue, particularly related with things like animal livestock. The thing with nitrogen is there's so many forms, and you might force doing one type of practice might result in additional ammonia emissions, but then you might reduce N2O emissions. So there's a lot more work to be done to kind of figure out what these trade-offs are on a large system basis. This is the total phosphorus of these 5 farms. The ones in Wisconsin look very similar, right? We see very much no difference, and I'd say the small differences you see are again due to measuring practices, but no removal of phosphorus in these. We do see some, this is from the study we did in Wisconsin, we do see some changes in percent solids. So you'll see some destruction. We're losing some of that to the biogas. There is some destruction there, so you will get a reduction. So the key thing in nutrient management is, one, the total mass of nutrients remains relatively unchanged. So the actual digestion process is not responsible for changing any of the nutrients, nitrogen, phosphorus. Again, there is going to be the reduction in carbon that we lose to the biogas, but we do see relatively unchanged. We still have to do your routine manure analysis and soil analysis. And where we see application benefits is maybe that you have less odor and you have less pathogen content. So those are the digester itself, that are the things that might cause benefit there. So then we have this fiber component and we have this liquid component. So a lot of people call these solids different things. I say most farmers or producers will call them the separated solids or digested separated solids. Some people will call them the fiber component. They all mean the same thing, however. The one thing about these is we're getting higher per unit volume. We have higher concentrations of certain phosphorus and nitrogen, and I'll show you how that balance breaks down in a second. And then after separation, we have this liquid component too. This is primarily used only for fertilizer, so still land applied. Whereas these solids now are used for bedding. They can be used for a number of other products. Hopefully that we'll see some increases in these products upcoming. So the one thing I wanted to show you is in the manure, right, so before digestion, we kind of had this 3-to-1 nitrogen to phosphorus before separation and digestion, right? So separation is really the key thing that changes this. So my nitrogen to phosphorus before I go through the separator is about 3-to-1. The liquid component then after the separator is about 4-to-1, and I tend to end up with this nitrogen to phosphorus of about 1-to-1 for the solid component. you can see the phosphorus content in the solid relative to nitrogen is much higher. So you can see that in a manure application system, I could really see some benefits. And one that if I separate, I can use lower cost application techniques for these liquids. And then for the solids, maybe the long distance travel where my lower phosphorus fields are, if I'm phosphorus limited, might benefit in using the solid component. This takes a lot of management, I will say. This takes a whole lot of management to realize these benefits. I've seen a lot of facilities, or even one facility recently tell me, you know, we were separating our sand and our solids, but after the sand component, separating the solids, the management to get the benefit from that just wasn't worth it to us. We weren't able to keep that end up. So I think it's really important that people recognize there is a benefit to this, but if you're not willing to carry through and make sure you track these and really use them and optimize your application methods, there isn't going to be much of a benefit to you. I do want to say things vary by different types of separator types. Of course, the moisture changes. That's somewhat important for people that use it as bedding. You can see all these systems, screw press, centrifuge. The blower is just a blower after a screw press. We're up here in, I don't know, 67 to 72% moisture on average. As you can see, these error bars, it can go up and down within there. Obviously, once I add like a dryer, this is a great way to use waste heat. I can really get this lower. The ideal for this might be, one, having a drier product in a bedding system, or two, we've seen that people are more willing to purchase some of these things for higher-end fertilizer products if they have a lower moisture content and a little cheaper to transport. Again, the separation, this is where this phosphorus part comes in. You can see here the centrifuge had a much bigger impact. About 60% of the phosphorus can end up within the solid portion as compared to these screw presses and things that were just over 20. Nitrogen is pretty similar for all the systems. The majority of it is maintained in the liquid, as you can see by this kind of brown portion there. I want to mention a few other systems quickly, just small-scale systems, community systems, and then talk briefly about economics, and then we'll open for general discussion. So there are some small-scale digester systems out there. There is potential for these systems. There's a few commercially available systems. We're still pretty limited on how the economics work out on these. They follow the exact same principles we've seen before, but they're smaller. So why don't we see them all around Wisconsin? Well, obviously still cost implementation. You know, the cost per farm is so, per animal increases so much for some of these smaller scale systems. I think we might see the potential as we move away from electrical generation, that maybe there's some viability of these systems, particularly even with electricity generation. If one, you can find a useful asset building reason to use the heat, or if maybe we see use of the electricity on farm, the one thing I really see as having potential is if we can get some of these lower cost cleanup technologies of the biogas. If we're able to realize one of those, the biogas could then be used in any natural gas system, and then we could really have additional options for small-scale use of the biogas. I'm sure a lot of you are familiar from Wisconsin with the Dane County Digester, which is a community-based project. You can see up here on the left, this is one of their feed tanks. In the middle is their additional feed tanks. They take manure from 3 different facilities, and then they pump that here, feed it into the digesters. So they have 3 1.2 million gallon tanks. They have the centrifuge to try to increase phosphorus removal into the solids. Then their solids are mandated to be sold outside of the watershed. So that is one case that we see that really there's a phosphorus change, is that if you have to transport the phosphorus outside to another place. If I were to separate this and just use this phosphorus on different fields within the same watershed, again, it's not going to have any impact to phosphorus use. But this system has been more potentially viable that you can, not only in this system where we're just combining 3 manure producing facilities, there is chances that eventually we'll see more, and we are seeing some more collaboration, that we have different types of systems, manure as a base with maybe a cheese production system or other kind of waste, organic waste producing system, that we can really combine the efforts, produce biogas, and maybe have more uses for heat, particularly in a more industrial setting. Okay, I wanted to leave a little bit of time here at the end to talk about economics. All right, so in the end, a lot of it just comes down to what we can and cannot afford. So there's been lots of work done. You can see over on the left, plug flow, completely mixed and covered lagoon systems. You know, a lot of this data is, I wouldn't use it maybe to compare the two. You really have to bid projects to understand. If you're really just trying to get a general estimate, these can be useful, but the scale and the types of systems that are available are very different in cost. You know, for one project, you might see someone bid from $2 million to $12 million, so they're very high range. It's very different in what those companies might provide for that amount of money. So it's important to look into the details. So some of it is more general information about economics are interesting, but I don't know exactly, they're only useful, you know, maybe in general planning. We do see that a lot of the cost is high for the connection to the grid, right? So that's a pretty significant portion of the finances that need to go to that, as well as the generation equipment, maintaining, you know, purchasing, etc. So really, it's kind of difficult to see how electrical generation is really maybe where we'll go unless we see a price change. One of the difficulties we see at digesters now is selling electricity at a price that can be profitable in a long-term contract. So a lot of people don't want to invest the money to build a digester if they can't get a long enough term contract that they can really guarantee a certain price point for a while. I'd say a lot of the contracts, you know, they might get 7 to 10 cents per kilowatt hour, 10 if they're doing really great, 7's maybe around average, but now that a lot of the renewable portfolio has been met in Wisconsin, we see a much lower offering price from a lot of the utilities. Okay, I'm stealing this particular information from Bob Nagle. We really don't see a lot of economics shared about these kinds of systems, understandingly so. But it was interesting to see in this particular case, he kind of added up what their income were. You could see from electricity a lot of savings in the bedding here. They really did the fertilizer value here. You might want to be careful with how you count that, I'd say. One, the fertilizer value is probably already there unless you're able to increase your price because of this system. They have additional heat. This number could really go up if you have uses for heat. Carbon credits, still quite a bit of money they're receiving there, tipping fees, and then tax credits if you have room to use those. The expenses, you can see maintenance is pretty high. Again, they're counting their manure application in here as part of their expense, which seems to make sense if they count, you know, the fertilizer was an income. They did decrease their manure application costs because of having the separation system. And then they have these depreciation and carbon credit fees, etc. And he noted that there's additional costs, right? Clean out, other maintenance things that might not be included in here. They're showing a pretty good return. Other facilities I know have paid off their systems in 4 to 5 years. But the one thing that I would say that I saw for his presentation that I see other times is that really optimizing these systems is becoming critical. So I've seen many facilities that have been successful and paying off their systems and being profitable, and many that have not. The ones that have been profitable have more likely had a lot of understanding of how their systems work and really did something to optimize their systems and get the payback that they wanted. Others don't have their systems as standalone, so when it costs them money, the money just kind of gets absorbed into the rest of the facility's expenses and revenues. And I see that they might not know that their system is functioning well or not, or that they might know it's not producing profits, but they're not doing the necessary, taking the necessary steps to really optimize what's happening. You can even see here, look at the price point difference when we talk about revenues in this year as compared to this year. We're almost, I mean, we're getting close to doubling what our electricity sales are. Why does this happen, right? Think about a wastewater treatment plant where they have people that operate anaerobic digesters on a regular basis. These people are educated for a long time. They go through a lot of training. They have to take regular certification courses and have a lot of information on how to operate these systems. On the other side, on these on-farm systems, we see that they're implemented and not a lot of training goes into allowing people to understand how to optimize the system and what's happening there. So, I see a lot of research going into kind of higher-end things, looking at different microbial communities, et cetera. But what we're really missing is figuring out how to optimize some of these systems. From feedstocks to mixing to making sure that your generator isn't down a number of times. I really see this as the big potential to increase and make some of these systems profitable that aren't at this point. Okay, the last thing I want to mention is some of the changes that maybe are up and coming, maybe are not, but the potential for advancement of these systems, particularly in Wisconsin and throughout the United States. One is the Digestate use. We're really getting low-quality things when we're, and fertilizer is important, but we really need to value it where it is. We need to remember and value it as a fertilizer component and develop uses for some of, particularly the solid components, that have higher end returns. Biogas use, we need to start thinking a little bit past just electricity generation. There's lots of other options out there, and maybe some of them have some much higher potential for revenues than we're seeing right now. The cleanup, I'm very interested in some of the new technologies maybe coming out to do biogas cleanup and working in my own lab on some new biogas cleanup technologies. I could see this as being the one major thing that could really change how biogas is used and the cost structure of how things might, where the end product might go. There could be policy changes. We've seen in some other states where they may increase their digestion systems because the cost for electricity is going to be a bit higher. When we're talking 7 to 10 cents per kilowatt hour, the system isn't going to be able to be maintained on that. Over in Vermont, they're talking something about maybe 14 cents a kilowatt hour, which they've done with policy changes. And that's really a promising thing. 14 cents a kilowatt hour. If you could ask all these digester operators if they made double on their electricity sales, it would be much easier for them to be profitable. And then potentially regulation. So as we move to air quality things, that there is evidence and that digesters have potential to impact emissions. So we may see, as things get more stringent in terms of the EPA on regulating emissions, we might see a little bit more of these systems go in for that reason. Okay, so I think I've taken up about an hour. We can open up for discussion or questions or anything anyone might be able to add. I hope that the information I provided was something useful today. I know I started a little basic. I just wanted to make sure everybody was on the same page, but I guess now, Scott, if you want to, I see some questions here. Rather than upgrade the methane to utility grade, why not burn on farm for heat and use in, say, aquaponics systems? I think there's a lot of interest in that, and a lot of people who are working on additional things that you could use the heat for. And so long as those can be profitable with that heat addition, I would say go for it. Some might say some of these ancillary components are another capital investment, and that you need to be sure that the payback is there. But I think that there's definitely potential to do some of those things. So recommend a specific lab to test the nutrient content in the Digestate in Wisconsin. We do a lot of testing here at our facility, but I also even send my samples sometimes when we're overwhelmed to the UW SPAL. They have a facility to test nutrients. It's just a manure test, so any Digestate can go anywhere. There's lots of different labs around the state. A few that come to mind are Dairyland and SPAL, and there's another that we sometimes send. But they're state approved, and there's a list of state approved labs out there. Anyone that does manure testing will do Digestate testing. It's a little bit different. The one specialized tests are more the BMP, biomethane potential tests. There's only a few of those around the state as of now. How many cows' manure does it take to supply power or electricity for an average household? That can vary quite a bit, but I think we say so. You can think in the Dane County system, there's about 2 megawatts will do about 2,500 homes. I'd have to do the math on that quickly. But that has maybe 4,000 or 5,000 cows there. So I don't know if you imagine.
Yeah, isn't it like 4 or 5 cows per kilowatt production?
Yeah, something. So maybe. I'll have to. If there's any other questions or discussion, we can do that, and I'll work this out on the side as we go. Dry digestion. So you know, you probably know of the Oshkosh system up in up by.
That's UW Oshkosh. Yep.
Yes, thank you. Up by Oshkosh, there's a dry digestion system. There's another going in another state, but in Wisconsin, I have some dry digesters that we've been working with additional feedstock waste. I know that the street division of the city of Madison has been interested in dry digestion. I know a few of my colleagues are working on dry digestion around the U.S. in different areas. I think a lot of the issues that have come up in talking about dry digestion are more feedstock transport. So the thing about digesters is that if you don't, manure has been such a popular choice, and as you can see, it wasn't because of its biogas potential, it's because it's located in one spot. So the cost of transport has really been limiting in terms of what is feasible or not. So the distance you can travel with certain types of waste. And so the problem with that is, you know, a lot of people see it as a really interesting option for eliminating maybe a landfill step and using those types of organic waste. But it's really the collection of those things that is still under debate about how that could work. You know, but they are talking about, you know, we already have collection systems that go around. There's potential to pressurize this gas and use them on a fleet of trucks, so that could really reduce collection costs. But there is a lot of work going into some of the things. I think this technology is established over in Germany, where they have, you know, 7,000 to 8,000 digesters there. At least half of them are definitely dry digestion systems. So they have quite a few over there. So there's a lot of technology that's available for that. Recommend a source for methane test equipment. Are we meaning like measuring methane? There's lots of different types. There's sensors that most facilities use at actual digestion sites, and those range and they're easy to find, but they can be costly, that's for sure. In our lab, what we use is something called a gas chromatograph. And if you're thinking of wanting to take samples and then just evaluate different samples, that's probably the kind of system you would need. Those can be expensive, but we use a system from SRI that's pretty cheap. Well, cheaper, but it's on the scale of $20,000 to $30,000. But there's different sensors. If you send me an email, I can help you find methane if you're just looking for a sensor just for a digestion system, or if you want to test multiple samples, I can give you the details one way or the other. Can the digestion process break down pesticides or other agrochemicals? So the thought is potentially. They're starting to have interest in looking at some of that work. I don't know that there's been a whole lot of it. Kind of like this, I kind of attribute it something to like the work we've done with pathogens. You can kind of the chemicals and pesticides are so different from one to another that you really have to start to evaluate them individually. Just like the pathogens, some that are easily broken down by heat are eliminated quickly, and others that are more resistant to those types of things are not. So it's going to have to almost be done now on an individual basis, and there is a little bit of work going on where I've seen both ways. One, that it's been successful for certain pesticides or chemicals, and others it hasn't at all.
Becky, you got some information from Bob Nagel. What size operation is that?
His facility, it might be 8,000 animals or something like that. Pretty large. Pretty large.
What size, economics, what size facility does it start to be economical? I guess the question where I'm going is, how small a farm is it economical to put a digester on at the moment?
It depends. So, I'd say most of the facilities, over 800, I don't think you're going to have a problem. 500 to 800 people have been doing some experience, successful, not successful. I think you might be able to make it work in that range. What gets more difficult is, these 200 cow farms. Some of the costs for these systems are still hundreds of thousands of dollars, and it just doesn't make sense to be at this point to do that. I've seen some that seem to be doing okay, but it's hard to tell if that's because of grants they've received. The small digesters, we're trying to do a study right now to look at how some of these are operating and seeing if they'll share some of this economic information with us. But from what I've talked to of the small operators, after the company has left, after the grants are done, after the research has been finished, they've struggled. So the smaller 200, 300 cows, it's still just, it's a huge risk, and I'd say a risk that's not favoring a positive outcome right now. I'd say if you're over 800 animals, you can feasibly work through these systems and get a positive payback. The more we go through it, the more we try to evaluate these things, and it changes every day, with how you can use the money. And they're coming out now, too, with some economic, some ways to better evaluate these systems economically. So to develop, a way to evaluate your system and a way to make a case to someone who would provide, the initial capital to be able to make some of these systems feasible and start up to get the loans that might be needed. Okay, so is there a cost barrier for small family dairies? Electricity becomes a major profit center. Can they sell milk at cost and live on the income from power generation? I'd say that's a long ways off. If electricity becomes a major profit center, selling milk, milk not being their primary, I guess I'm reading that as milk becoming not the primary export of their up their farm. I don't see that as being the number one thing here. A lot of the facilities that we see too mostly will maintain their animals to produce milk, not to change manure characteristics or things. You know, if the price changed significantly, that might be possible, but in these systems, the price for the energy they're getting is nowhere close to the amount of money they're getting for the milk. So I think that's probably a long ways off of that ever potentially happening. Not in our lifetime, I don't think.
Well, and I think the one way to look at it is we have a couple hundred farms that are greater than 500 cows, but only 20 or 30 that have digesters on them. So if it was very economical, you'd see many more installations. A lot of these people tell us that the reason they put them in primary was for odor control from neighbors.
Yeah. And that's for one thing that I've heard.
Yeah. And that, you know, they're just trying to make them break even and not lose a lot of money on them.
And I could see with, you know, as more of them go in, you know, we've talked a little bit about the battle for feedstocks that could ensue to go into them, and that might, you know, reduce revenues from them. I don't know that there seems to be, although there is abundant amount of feedstocks around Wisconsin, I don't see it as being a big issue for changing the face of dairy anytime soon. Although I do see it as potentially a way to receive additional revenue streams to maybe pay for additional components that might help you better manage manure or be a better environmental steward.
Okay, well, we're coming up on the end of our time. I'd like to thank you, Becky, for stepping forward and putting this on.
Thank you. I appreciate the help, Scott.
And if anybody has any other questions, you can email them to either myself or Becky, and we'll try to answer them. So with that, we'll conclude this webinar, and we appreciate that. I will be sending out a post-evaluation afterwards, and we'd really appreciate it if you'd answer that to give us feedback. So with that, we'll call it a day. Thank you.